Hi guys, welcome to summer assignment part 2. This is a continuation of Baby Chem Boot Camp and a review of what you learned during Chemistry 1. This correlates with Unit 2 in the Brown-LeMay textbook and the summer assignment part 2 outline that has been provided separately. All right, now that that's said, let's get started. Okay, so this unit we're going to be talking about atoms and elements. So we're going to start way back at the beginning. Now, in the outline and in Brown-LeMay's Unit 2, you will find more historic information about scientists that I'm not going to go over in the lecture. You can look at that in the outline. And also I think I'm going to provide a separate video about that. I would rather keep to the science in my lectures. But we do need to talk about atomic theory here. We have 3 laws that the atomic theory is based upon. The first one is the law of conservation of mass. You've probably heard of this law in another class, especially if you've taken physics. And that is that matter can neither be created nor destroyed. And so whenever we have a chemical reaction, we are going to take matter, break it apart, and then form it together in a new combination. So an example of this would be Legos, right? Hopefully we all played with Legos when we were kids. And so you have a pile of 20 Legos and they're all separate and you combine them together and make a house. So that would be an example of a synthesis reaction. And the house needs to be made of all the Legos that were there in the pile when you started. You didn't create any new Legos and you didn't destroy any Legos. Let's say you take the house apart and build it into a car and a tree. So that would be another type of reaction. And you didn't destroy any of the Legos. And you didn't create any new Legos. You used exactly the Legos that were in the house to make 2 new things. So that's what chemical reactions are. We can't get rid of those original Lego blocks, which, by the way, are analogous to atoms. Laws of constant composition is that when we do have a combination of atoms coming together, that combination will always be in the same ratio. So our quickest example that pops into our head, water, right? I say water to you and a lot of you might automatically think H2O. 2 hydrogens and 1 oxygen. It doesn't matter if we're drilling at the North Pole and pulling up water molecules that have been frozen for millions of years. There are going to be 2 hydrogens to 1 oxygen. Or if I set a bucket in my backyard during the summer rainstorm that will happen this evening and collect that water will be 2 hydrogens to 1 oxygen. Our example here on this slide is carbon tetrachloride. No matter where we look at carbon tetrachloride on the earth or in history, it will be 1 atom of carbon or 4 atoms of chlorine. That is carbon tetrachloride. It's nice to kind of have something that's constant in the world, right? And then we have the law of multiple proportions, which is if you have 2 elements, we're going to call them A and B, and we combine them to form more than one type of compound. The mass of B that can combine with a given mass of A are in a ratio of the smallest whole numbers. So our examples, we have water again. If we have H4O2, we can reduce that, right, to H2O. And if we have H2O2, right, and compare that to H4O4, H4O4 can be reduced to H2O2. And this is based on oxidation numbers and mass, which we will talk about more later. So we take these laws and we get to Dalton in the early 1800s, and he creates our formal atomic theory that we will use for the basis of all chemistry. So let's take a look here. Each element is made out of atoms. Check. Atoms of each element are identical, but atoms of different elements are different. We know that that's based upon the number of protons in the nucleus. Compounds are formed when atoms combine. And chemical reactions are a rearrangement of atoms, and that atoms cannot be created nor destroyed. So I'd like you to pause this video right now and take this slide and the last slide and create either an outline or a mind map or a picture or diagram, something that brings those 3 laws and the 4 principles of atomic theory together so that you see the cross concepts that are going on there. Remember, this is a review from Chem 1, so I hope we all remember J.J. Thomson and his cathode ray tube experiment. Little review that he took gases, pure gases, and put them into cathode ray tubes. And what that meant was they were tubes with a charge. You can kind of picture them hooked up to a battery. And so that put a charge through the gases, and the gases lit up, right? Like the cathode ray tubes that we used in Chem 1 with the spectrometers, right? And we got to see the full spectrums that of light that those charged gases were putting out. Hopefully you remember that experiment. It's a fun experiment. All right, so the gas lights up, and so we had a negative cathode over here and a positive anode over here, and he saw that the gases lit up when they were exposed to electricity. And then he brought over a magnet, and when he put the positive end to the cathode ray tube, the electrified gas, the charged gas, turned towards the magnet. And when he did the same experiment, I'll draw it down here. Ah, that's terrible. I gotta redraw that. Miss P. Okay. There's a little bit better cathode ray tube. Okay, and so we've got our negative end here and a positive end here. And when he brought the magnet over, but he put the negative end, then that charged gas moved away. And so he said, hey, wait a second. That means that there are positive and negative charges here. And he came up with his plum pudding model. We don't eat plum pudding anymore, so a lot of your Chemistry 1 teachers probably made an additional analogy to a blueberry muffin or a chocolate chip cookie, of this idea that you have a 3-dimensional object with things dispersed throughout the object. And so if we were to draw this, right, J.J. Thomson said that we had this sphere. I'm drawing it 2-dimensional, but it's really 3-dimensional. This sphere of positive charge. So this is just a dense positive charge. And that there were electrons throughout. So remember, this is three-dimensional, so the electrons would have been inside and outside and all over, just like a blueberry muffin. There's blueberries inside and on top and outside and all sorts of things. That makes me hungry for a blueberry muffin. I haven't had one of those in a while. All right. Then the next experiment, do you remember? Bill experiment. So Rutherford, right on the heels of Thomson, said, I wonder what else is going on inside that atom. And so he took a piece of gold foil and surrounded it by fluorescent screening that when hit with energy will glow. And so he shot alpha particles at the gold foil. And so when the alpha particles hit the gold foil, most of them did what we expected and went straight through the gold foil. And we can see that spot lit up on the fluorescent material, and we have that beam of alpha particles going straight through. And we can see the intensity there is the biggest. But what else happened was that some particles went at a little bit other angles, including completely off to the sides and lighting up the fluorescent screen completely off to the sides of that gold foil experiment. So let's look at what that means. So here in the background, these little yellow circles represent the gold atoms. And we can see how they're nicely arranged as they would be. And these red lines represent the alpha particles. And so the first one that we look at is this alpha particle that goes straight through. And I drew that poorly, so I'm gonna erase it. Okay, I was not exact enough. So we see here this alpha particle, this guy right here, that goes through the spaces, this guy too, in between those gold particles. So what that proved to Rutherford is that there is lots of space. And why we can say lots is because that was the most intense arrow. So this arrow right here, I'm sorry, not arrow, point on the fluorescent screen tells us that there's lots of space. It was the most intense, largest spot. So we know the most alpha particles went through those spaces, and it tells us that there's space between the gold foil, because if there wasn't space between those gold atoms, they all would have bounced back, right? And then these ones that go to the sides, like this guy, whoops, tells us that we have a nucleus and that those alpha particles were hitting the nucleus and bouncing off. And then here we even have, forgot to show this guy earlier, we even have ones that bounced directly back, didn't go through the gold foil at all. And so that told Rutherford that that nucleus has mass. It has enough mass to make that alpha particle completely ricochet back in the opposite direction. So this experiment led Rutherford and Thomson to realize that there was a nucleus in the center and it had mass, it had density, and that there were electrons floating around in the outside, and there was a lot of space between them. And that was a novel idea back then, because even though they knew atoms were making up matter, they thought these atoms were compressed together. You know, I hit this table and it's hard. My fist doesn't go through it. So they thought they meant that those atoms were solid, but they are not. There's space between them. All right, so now we're going to talk about the size of the atom. So Rutherford experiment led the scientists of that time to say, so what is the size of the atom? And then many more experiments followed as technology developed using X-ray, magnetic imagery, and things like that. And so they came to realize that the nucleus was very small compared to the size of the whole atom, and that most of the atom was filled with space. And that is where those electrons hung out, which was interesting because the electrons were also very small. So let's get some ideas here of size. So if our atom is 1, that's kind of hard to see. I'm going to switch back to my red. All right, our nucleus is going to be 1/10,000th the size of the atom. And a proton is going to be 1/100th the size of the nucleus. And an electron is going to be 1/1,000,000th the size of that atom. So the atom is, yes, it's very small, but it's relatively big compared to the nucleus, protons, and electrons. Oh, and neutrons are the same size as protons, as we will see in the next slide. I would like you to pause this video and come up with your own analogy of these sizes if you start with that an atom equals the size of the Earth. And the Earth is actually 13,000 kilometers. We're using kilometers because we're in metric system here. The Earth equals 13,000 kilometers. So I want you to pretend that an atom has a diameter of 13,000 kilometers, and I want you to figure out what would be analogous on Earth to a proton and to an electron. Oh, and the nucleus, right? So start with the atom equaling a diameter of 13,000 kilometers. How big, what would be equal to a nucleus? What would be equal to a proton, an electron at that scale? All right, pause and do that activity. Okay, if you would like that last activity, you can take a picture and email it to me, or wait until we get back into school and show it to me. I would love to see it. It's not a graded assignment. I'm just always curious what students choose to represent the atom to the scale of the Earth. All right, let's refresh our memory of the chemist's shorthand. Not very complicated here, but something some of you might have not thought about in a while, and to refresh our mind. So when we write out atomic symbols, we are going to put the symbol of the element from the periodic table down first in a capital letter. If we have a symbol that is two letters, like copper, we're going to use a capital and a lowercase. Because remember, if we have two capitals together, that's going to be two different elements bonded together. So if I have a capital C and a capital U, that's copper and uranium bonded together. So we want to make sure we capitalize appropriately. Up top in the upper left-hand corner, we're going to put the mass number, which is on the periodic table. And our mass number is our number of protons plus our number of neutrons. Down on the lower left-hand corner, we're going to have our atomic number, which is just our number of protons. And we know, if we want to know how many neutrons this guy has, we are going to subtract the atomic number from the mass number. So this potassium has 20 neutrons. And in this upper right-hand corner, this is where charge would go. Now, because this potassium has nothing written there, that means that the charge is neutral. So if nothing's written, it's neutral. If there is a charge written there, then we need to change the number of electrons. So that this potassium is neutral, that means that our number of electrons equals our number of protons, which means that we have 19 electrons for this potassium. So, quick reminder here, electrons are really small, negative 31 exponent there, very, very small. We usually consider their mass to be negligible. Chemists will not say electrons don't have mass. We say that in Chem 1 just to oversimplify. But we do go with electrons have mass. It's just negligible in our calculations. And of course, the charge is -1. Protons and neutrons are the same size, still very small, but bigger than an electron. And protons are +1 and neutrons are neutral. Remember that the job of the neutron is to keep protons from repelling each other because they're all positively charged in a very small space, and to keep those protons stuck together inside that nucleus. All right, Avogadro followed Thomson and Rutherford, and he was our guy who invented the mole and Avogadro's number, which we will talk about more in the next unit. I know you're excited, but 1 mole equals 6.02 times 10 to the 23rd atoms, particles, molecules, formula units, but it also equals 22.4 liters. And like I said, we will talk about Avogadro's number more in Unit 3, and then we will talk about Avogadro a lot in our gas unit much later in the year. So when we have the same temperature and pressure held constant, gases that are not being compressed or expanded, that are held at the same volume, 22.4 liters, will have the same number of particles. So here's an example: helium, nitrogen, and methane. And we see same volume, same pressure, same temperature. The mass will be different because each one of those atoms weighs a different amount because it has a different number of protons and neutrons. But we will have the same number of molecules. All right, hitting the periodic table, you will come to learn during AP Chemistry that the periodic table is really a giant mnemonic device. It is not perfect. There are some flaws to it because the periodic table is putting things that happen naturally in the universe, whether human beings were here or not, into patterns for humans to be able to understand those elements and be able to utilize those elements. Okay, so let's talk about the periodic table. So the periodic table is really just a giant mnemonic device. Let's talk about the periodic table. So the periodic table is really just a giant mnemonic device. That being said, it has flaws to it. A lot of people want the periodic table to be perfect and have this patterns that are perfect without any exceptions. Well, the thing is that the information that the periodic table holds is things that would be happening naturally in the universe, whether human beings were here or not. And so the periodic table is just our way of taking these elements and putting them into patterns that help us understand them and utilize them. So the patterns are fantastic, but there are some exceptions and we will learn them along the way. So elements are put into the periodic table based on their atomic number and their properties as they fall into their groups and families. And hopefully you remember in Chem 1 what groups and families, those vertical columns, have in common is the number of valence electrons. And that gives elements their ability to bond and a lot of their characteristics and behaviors. And so that's why we call those vertical columns families, because all the elements are a little different. They're individuals, but they behave like they're related to each other, just like you and your family. You're your own person, but you have some characteristics and properties that make you similar to the other people in your family. So when we look at this, the big ones that we want to remember is that column 1 are our alkali metals, column 2 are alkali earth metals, column 7 are the halogens. That's our second to last one on the right hand side, and our last column, which most people remember, are our noble gases. Going horizontally across the periodic table, the rows are periods, and those represent the energy levels that our electrons in. So as we add new energy levels, we know that the atomic radius gets bigger and those electrons are further out, so they have greater shielding, which means that their electronegativity and ionization energies decrease. We will review that further. Don't stress if right now you're like, wow, that was a lot of information that I kind of remember from Chem 1, but I don't. Don't worry about it. Just making connections to all those great things that we learned. We will talk more. All right, let's look at the periodic table. All right, we have all those metals. Metals are the guys to the left of the staircase, right? That invisible staircase that we have right here. Oh, my pen stopped working. Okay, and of course, hydrogen hanging out here. We know he's not a metal. So all these guys are metals. They're all going to conduct electricity and heat. They all want to lose electrons and become cation ions. Remember, cation ions are positive. Cats have paws, so cation ions are positive. Because the metals are going to give electrons to those nonmetals in those ionic bonds. So when they lose some of that negative charge, they become positive. Metals are also malleable. That means we can shape them, and they are ductile, which means that we can pull them into wires, which is great because that gives us all our fantastic technology, right? Without those metals. Non-metals, here we have hydrogen again, non-metal. And now we're to the right side of the staircase. We see that there are actually fewer, by quite a bit, non-metals in the universe than metals. Non-metals are brittle. If we strike them with a hammer, they're going to crack or crumble, whereas those metals were malleable. They are going to gain electrons, right? So if I draw this guy again, the metals are going to give them electrons, and that's going to make them turn into anions, and they're going to be negative because they're gaining negative charge. And our mnemonic device here is a negative ion is an anion. And they can form their own special little bonds with each other, covalent bonds, where they share electrons because they're so friendly with each other. So a very nice example over here would be carbon monoxide using carbon and oxygen, both nonmetals, and they're going to share those electrons covalently. All right, then we got the little staircase here, right? Our semi-metals or metalloids. And some people don't like them. They're like, come on, are you a metal or are you a non-metal? Well, they show characteristics of both metals and non-metals, right? They're in this kind of zone where the metals and non-metals meet. They will also be brittle like a non-metal, but they're going to have a metallic luster like metals. They are fair conductors. Some of them conduct magnetism, electricity, and heat much better than others, but they're not awesome. Think aluminum, right? Aluminum, this guy right here, he conducts electricity a little bit of heat, which is good, helps us with cooking. And they make, all of these guys make great alloys with other metals. So when we take a pure metal and mix it with a metalloid, we end up with alloys that we can do really great things with, because pure metals can be very hard, very heavy, right? We add aluminum to a lot of pure metals to make it lighter and more manageable than they would be in their pure states. So chemical bonds, we know that chemical bonds are different elements being held together. Molecules are covalently bonded atoms, so that means that we've got non-metals here when we're talking about covalent bonds. And we've got diatoms. Diatoms are atoms that, even in their pure form, they're hanging out with other atoms just like themselves. They don't want to be alone. They want to bond to another atom like them. So our easiest example is hydrogen, right? So hydrogen is a diatom. If you have a tank of pure hydrogen, those atoms are going to hang out together. There are 7 diatoms. Hydrogen being one of them. I'm actually going to turn to my periodic table, and you want to start with nitrogen, number 7, and make a 7. So we're going to have nitrogen, oxygen, fluorine, chlorine. Oops, I forgot that's supposed to be a comma. And bromine. And I can fit them in there iodine. So we have 1, 2, 3, 4, 5, 6, 7. There's our 7. And so when you look at these guys, nitrogen is number 7 on the periodic table. If you look at these guys, they form the number 7 on the actual periodic table. So those are our elements that when they are in pure form, hanging out by themselves, they're going to bond with atoms. All right, symbols. Remember that when we make a chemical formula, we are going to write our symbols. Here we have carbon and oxygen, and the little number down below is a subscript. Some people get that prefix confused. Think sub means under, like a submarine. Super means upper, like Superman flying up above. So a number down here tells us how many of this atom we have with this atom. So carbon dioxide has 1 carbon for every 2 oxygens. That will always be carbon dioxide. And a structural formula actually shows individual bonds using lines. So here we have carbon dioxide, and we see here that carbon dioxide requires double bonds. Does anybody remember the Vesper shape here that we have? This would be linear. That is not in this unit. Just again, making those connections that we need to have in chemistry. Okay, ions. Ions are when we're going to have ionic bonding going on. We already covered cation is going to be positive. Anion is going to be negative. This is because the cation is giving anions electrons. Ionic bonding is the attraction between these atoms because one has transferred an electron to another. The metal has transferred electrons to the nonmetals. And ionic solids are called salts. And our favorite example right off of the dining room table is sodium and chlorine, right? Sodium gives chlorine 1 little electron, and they become steadfast friends. And we have sodium chloride. Naming compounds. This is really important, guys. Please make sure that you practice this over the summer so that you are ready to write formulas and to see a formula and be able to write the name. We will not be going over this during the year. This is something that you've got to be ready to go with. So let's review. First, we always write the cation first and then the anion. That's not too hard to remember because metals are on the left and nonmetals are on the right, and we read left to right. So we write it in the order we see it off the periodic table. A monatomic cation, we just write the name of the element. Monatomic ion, anion, we take the root word and we add ide. So instead of chlorine, we write chloride. So calcium, being the cation, kept its full name, and we see it there. But the anion gains that ide ending, so it becomes chloride. So CaCl2 becomes calcium chloride. Polyatomic ions, I will give a separate link of polyatomic ions for you guys to review. I don't like using the word memorization. I prefer the word review, but it would really benefit you to come up with patterns that would help you basically have those polyatomic ions memorized so that you can retrieve them. You will not be given a polyatomic ion list during labs or any assessments. So, yep, I say that right here. Memorize the list, but know the trends. So cations have the ending of -ose or -ic. For example, iron plus 2 is going to be ferrous, and iron plus 3 is going to be ferric. Cations form from nonmetal atoms that have the ending IUM. So ammonium ion, and ammonium is all nonmetals. Oxyanions are anions with an oxygen, and those are those polyatomic ions that you memorized in Chem 1, and they're going to have those ate and ite endings. So for example, here we have chlorate and chlorite, and how you know the order is that the greater number of oxygens is going to have the ate ending, and the fewer number of oxygens is going to have the ite ending. So you can kind of think of it as a hierarchy, right? Ate and ite. There's a very nice chart in Unit 2 of Brown-Lemay, and if you don't have the textbook yet, that's okay. You can Google these ending charts and find them. I will also try to post that to the website. Naming compounds, binary ionic compounds, meaning that you have more than one. Metal is going to form the cation, and we're going to use Roman numerals for our transition metals. Okay. So we know that lead has more than one oxidation state, but in this situation, we don't know what it is. We just have a formula here. So here we have 1 lead and 2 chlorines. We know that chlorine is a -1 charge because it is in the 7th column on the periodic table. And so in lead with 2 chlorines, we see here that our total charge on the chlorines, I don't want to write a C. I was thinking chlorine, so I was starting to write chlorine. All right, so our total charge here is going to be a -2. Well, for chlorine to each get those guys, we need this to give 2 electrons. There's only 1 lead atom, so it's going to be the guy that gives those 2 electrons. And that Roman numeral tells us charge, not number, of the cation. So our Roman numeral always goes with our cation, with our metal. So PbCl2 is lead 2 chloride compounds, which means that we're naming compounds that only have nonmetals in them. So the first element just gets its name. The second element is going to be named the same as if it was an anion in an ionic bond, which means that we are going to put on the "ide" ending. But then we're going to use prefixes to tell us the number of atoms that we have present. So we have mono for 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa for 6, hepta for 7, octa for 8, and Mono for 9. So here we have an example of P2O5. So that's going to be diphosphorus pentaoxide. And the root word decides the vowel. So notice we lose the A there because of the oxide. The root word trumps the prefix. Our one exception to the rule is that we do not use mono for the first element. We only use mono for the second element. So a good example here is carbon monoxide. Okay. All right. Then something a little bit new is naming acids. We talk about acids in Chem 1, but we don't name them as much. We kind of just tell you, hey, here's some common acids like hydrochloric acid, and you sort of just memorize them. Also, you already have a knowledge of them. Reminder that acids are substances that produce hydrogen ions when they're dissolved in water. All acids begin with H in the formula. So we always put the hydrogen first when writing an acid. So if we think about like methane, right? The hydrogen is in the second spot. This is not an acid. But if we think about hydrochloric acid, we have the hydrogen written first. That's an acid. So when we have an acid, we always put the hydrogen first in the formula. Oxyacids are acids that have an oxygen present. So an oxygen is in the formula. We write the name of the anion. Okay, so the second guy, the guy that's going to have the negative charge. But we change that "ide" ending, there should be an E there. We change that "ide" ending to "ate" or "ic" for an acid, and we change "ite" to "ose." So here we have chromic acid, and here we have nitric acid. So those endings that we normally would have had, we're going to change for our acids. And then binary acids, where we have no oxygen present, much easier, and ones that you're pretty used to. We're going to change the suffix "ide" to "ic." So here we have hydrochloric acid, sulfuric. I don't know why that "ic" is missing there. Let's put that in there. Sulfuric acid and cyanic acid. CN is cyanide. All right, let's do some practice. Please pause and try these guys on your own. So here's the answers. I just want to point out a couple of things. I'm going to pick a different color here for us to take note of. So of course we had 2 transition metals there, so hopefully you got your Roman numerals in. Remember, you have to figure out your charges, and these guys were polyatomic ions, so you needed to look at those. Also notice the endings on our polyatomic ions. We've got an 8, 8, 8, right? We're not using those ides when we have polyatomic ions. Notice that the nonmetals are using prefixes. And maybe you noticed this guy right here and went, what the heck? Yes, this is a noble gas. Noble gases can bond with other atoms. Thought I'd throw that in there to kind of give you a taste of the things to look forward to in AP chemistry. Chem 1 lies unfold here in AP Chem. All right, let's take a look at this. This one's going to be a little harder. Here's some acid formula writing. I know you haven't had this before. That's why we're practicing it here. So I want you to pause, go back to that other slide, and give this a try. So hopefully that wasn't as hard as you initially thought it would be. It takes a little problem solving and using that list of polyatomic ions. Basically, when you have an acid, you're going to use that polyatomic ion list and look at those charges and do swap and drop to get the charge that, or the number of hydrogens that you need. So if we look at number 6 here, right? Oops, my pen. All right. So if we have, that's not the one I want. If we have phosphate, which is PO4, -3, then we do that swap and drop, and that's how we get the 3 hydrogens, and we put hydrogen on the front because it is an acid. But I threw in a couple little harder ones here with our acid prefixes. We've got di, hydro, per, right, which changes those meanings a little bit. So we know here we've got chromic, so we had a chromate. Well, what does di mean? Di means 2, right? And so that changes our formula a little bit. If we have 2 chromates, we actually end up with Cr2O7. We'll get more into this formula writing in the year. And so we still have that -2, which gives us 2 hydrogens. So this is just to give you a taste of acid writing. We actually will not do a lot of acid nomenclature. It's just so that as things come up when we do reactions, especially in labs, you know how to handle it. So same lines as our regular nomenclature. We're going to use the same prefixes as we would with covalent bonding. We're changing those 8s to X, and we're making sure we write the hydrogens up front. All right, let's do atomic identification practice. You will need a periodic table either on your phone or another tab on your computer or print it out. Let's pause and take a look. Okay, here's our answers for that last slide. On our left, we have all our atomic symbols. Notice that we did get the charges written in there. And to figure out our number of electrons on those charges, basically what we're saying is if there's a negative charge, then we are going to be adding to our electrons and have more electrons than we do protons. And if it is positive, then we are taking away from our electrons and we're going to have more protons than electrons. We cannot change the number of protons. We can only change the number of electrons. Also notice that some of these atoms that we're talking about here have a different mass than you would find on the periodic table. So for example, strontium on the periodic table has the mass of 88. And this mass that you were given isn't incorrect. It's just an isotope. Remember, isotopes are atoms of the same element with a different number of neutrons, and therefore their mass is different. So this particular strontium sample is going to have 42 neutrons, where on average a strontium sample would have 50 neutrons in their atoms. So those are isotopes of each other. There will be supplemental information with this lecture. I'm going to include a list of polyatomic ions, a video on scientists, and some additional nomenclature practice and resources. Some people will need more practice than others. That's okay. Just be prepared that when school starts, you have your nomenclature down. All right, guys, go ahead and enjoy some summer.